be lots to read about Randolph's bio, but I will just say that his educational background is both in architecture and building conservation, with degrees from Harvard College and Harvard Graduate School of Design in the United States and the Institute of Advanced Architectural Studies in York, England. He's co-author of the book Amos Keag, published in 1978 by Random House and still in print, and also of Satanic Mills, published by Save Britain's Heritage. It was this early work on the great multi-story brick and stone factories which were subjected to the substantial vibrations from the power looms, which in the United States were traditionally located on the upper floors of the mill buildings, that launched his later life's work on earthquake-resistant forms of masonry and timber construction worldwide.
You know, we've been seeing these pictures of collapsed buildings in Van, Turkey. Pancake collapse. The modern buildings that we've been dealing with, ironically, the reason why I called the lecture Puka is Kacha and Kacha is Puka, those of you who are not familiar with India, a Puka house is a strong permanent house, and it's become a synonym for a concrete house. And a Kacha house is like one built out of bamboo, or now also timber and masonry is not considered as strong as a Puka house. And here we are seeing the Puka buildings, so-called Puka buildings, collapsing. Not only just collapsing, but a pancake collapse seems to be invented by reinforced concrete slab and frame construction, because then anybody who has survived is under layers and layers and layers of armored concrete. And it takes, as we know, a challenge at best to get everybody out while they're still alive. That earthquake in Van just recalls the one just 12 years ago, two of them in Turkey, further to the west, where just scads of reinforced concrete framed buildings had collapsed. And then just a few weeks later in Sikkim, same images. And it's interesting to kind of look at a report that has come out of the Sikkim earthquake and take a closer look at one of the things that were observed. And here you see the executive summary. The recent reinforced concrete, RC, is reinforced concrete constructions do not have earthquake-resistant features. I mean, that in some ways just understates the obvious. It's worse than that, as you'll see a little bit later. But then when you see why, you have to ask yourself, well, if there are only two structural engineers in this part of the world, how can you even expect them to understand it? Well, then you say, well, aren't these and other types of buildings the same? I mean, that people would have at least a basic knowledge and put these buildings up. What I've come to realize in doing this work is that reinforced concrete construction is a very sophisticated, knowledge-based form of construction, and the absence of that kind of extra training that it would take to really understand this material has led to a crisis when it comes to earthquakes. And earthquakes are, in fact, unique. Most people will probably not realize that the building code in this country and in Europe, and in anywhere there's a building code for building construction, is predicated for earthquake risk on using lower force levels than actually are expected to occur in the design level earthquake. And the reason for this is that it would be totally uneconomic to expect the buildings to remain within the elastic range. And I showed this picture because I found this, of course, on the internet. The collapsed concrete building, and what's that behind it? You can't say that building went into the earthquake in good repair. But there it is standing, a traditional building. And in this very same report, it says the traditional ekra, they call them their ekra houses, which are timber and infill type of construction. I think more of a wattle and daub infill. But they did extremely well. Well, did people have training to do those houses? No. It's inherited, it's handed down, it's the same kind of thing. So look at the schools. We know that schools is this building type that has suffered in earthquakes out of scale with almost anything else. And so it's become the focus of the bank's attention, as well as almost every other agency and NGO that's involved in post-earthquake work. The schools in the older traditional form did better than reinforced concrete, the puka houses. This is a situation what I'm saying after having looked at this for the last 25 years or so, I realized the essence of the exercise of looking at the older buildings is what can they teach us? And how these buildings, in fact, are modern. That's why I called one of my websites Traditional is Modern, because it's time that we see the continuum in building construction to really understand the nature of what we're dealing with. This is Srinagar in Kashmir, the Indian part of Kashmir. These seemingly rickety, tumble-down buildings, as somebody in the 1880s reported in a travel document after the earthquake of 1888, said these rickety, tumble-down buildings seemed like the wind would blow them over, but they went through the earthquake better than the palace, which was just built in unreinforced masonry. And that building kind of says it all. How could something like that have any strength? Well, when you look at what the construction is and realize that this was on a very soft soil site. This is not earthquake-resistant construction per se. It's not deliberately earthquake-resistant. It's a way of holding the buildings together from differential settlement on a soft soil site. Not unlike Mexico City, Srinagar is on a prehistoric lake bed. And you can see, if you can hold a building up in a three-point support on 3 points like that, that's masonry, bearing wall masonry. You're really talking about something that is held together by those strengths. And when you look at how it is constructed, you can begin to see that what's interesting about this is there's no vertical timbers. This is horizontal lacing only. I've come to realize that that's really actually very important for this type of construction. Yet, in the building code provision that they developed for this in India, they stuck in a requirement for a vertical rebar. And, it's like, wait a minute. And in my book here, I said that's the one mistake. I mean, it's sort of, I took the liberty to criticize the most foremost engineer in all of India, Anand Arya, who wrote that code. Because I think that they failure to understand that this is a bearing system and that it has to move over time and maintain that overburden weight is a characteristic mistake that engineers today often miss about how masonry works. So there you see where those frames are. They're at the floor level, gripping on inside and outside the wall, with a joist that run all the way through the wall to the outside, and then a cross side is picked up by subordinate joists, cross pieces of wood, and then above the window head and at the next floor level. These buildings are not small. So you can see on the exterior how they're laced together, which is kind of nice to actually see. One of the problems with the reinforced concrete and other forms of construction where we embed even retrofitted buildings, you embed the rebar in the wall, you won't see it. You can't see it, you can't know whether it's there, has it rusted away like it did in Haiti, so on and so forth. Here's what happens to buildings there if they don't have timber lace. And this is a good example of a difference, even a cultural difference here, because the building on the left is Srinagar. With the timber lacing, you can see it even sticking out at the edge there. And you see how the building is tipping and leaning? That's because of that soft soil site. And the building on the right was photographed in Kathmandu. Well, Kathmandu had an earthquake in 1934. And here is a picture of the buildings in central Kathmandu, in Patan, which you could go see there today, but you probably don't realize that, in fact, those buildings you see there today are new. Rebuilt after a devastating earthquake took them many of them right to the ground. And they are presented, here you see, in fact, the same monument on the right, you see here, and then move forward, you see that same monument right here, the position here there. So you can imagine there's a lot of masonry in those buildings, but it took it right down, because most of it was behind the brick, it was a rubble stone in that case. Well, this form of construction, which the best word I found for it was tak for Srinagar or Batar in Pakistan side of the border, is embodied in the Indian Building Code. But they also missed, in this illustration here, the sandwiching of the joists at the floor level. But I think it may have more to do with the casualness of that sketch. Now the other type, which is going to carry through the rest of my talk, is the Daji Dwari. That is an interesting form of construction because it is almost so universal. It's a frame-based, a timber frame, complete timber frame. And here we see it in Herculaneum in Rome. They dug up a building that was believed, when they restored it, to be a timber frame infill wall masonry building. They believe that Vitruvius had identified this as opus creticii. And what's interesting is that it had a negative connotation in the book, but he had no illustration. So I actually think that he didn't mean this type. I don't know, though, because this I have found to be very positive. And it's a cheap form of construction. You only have a thin membrane, as you'll see as we go along here. This is in Srinagar, a building demolition project that shows you we have this gossamer thin wall, one layer of masonry, a timber frame embracing it all. Now, how can that be better than reinforced concrete? How can that be better than other forms of construction in an earthquake? It just seems counterintuitive. This form on my first trip to Srinagar is still being used. You can still find it. I'll mention it a little bit later about Pakistan. But when there is a timber supply, and that's of course the big argument, well, timber is really expensive. Well, excuse me, we'll grow some more. It is a renewable resource, and it's just time that people cope with the fact that they've exploited it without renewing it. It is also in the Indian Building Code, though, and here it is shown. And what is interesting is that in two places in the world I've been able to find it where it was invented, developed, and mandated as earthquake-resistant construction. First was in Portugal after the great 1755 All Saints' Day earthquake in Lisbon, where it became named the Gaiola and was required by law for the reconstructed area of downtown Lisbon. And there's a picture of a building where the plaster had been removed from the wall, showing this timber frame with infill. And that, in fact, this research that the Portuguese government did on this shows incredibly good seismic behavior, where the amount of energy dissipation these walls can provide is shown in this graphic there. The thrust of the machine never took it to a declining strength. So moving on back to contemporary earthquakes, there is the Kashmir earthquake of 2005, which was centered in the Pakistan side of the border, but did cause damage in India. But the 80,000 or so deaths were almost all within Pakistan. And this is a building in downtown Islamabad, remote from the damage district. Remote. And it took it right to the ground in a pancake, and so that you have scenes that are as heartrending as that. People pinched and stuck underneath buildings. Luckily, when they get found, they can be saved. In the damaged district itself, the town of Balakot was basically leveled. The only identifiable shapes left were the tin roofs. This was unreinforced masonry block construction where the blocks, if you look carefully, look almost cubic rather than rectangular, making for a very poor kind of prevented masonry. And then the floors were concrete, so they're heavy buildings. I did get into the rural countryside, and that became very interesting because here is essentially their store in the center of a little village called Thub. And that collapsed. It was 3 stories to begin with. But right nearby were 2 buildings that were Daji construction. Daji Dwari means patch quilt wall. And they came through just fine. And across the border in the India side was this one. It kind of shows you how the Daji construction can even form a truss across an opening where the unreinforced masonry below it failed. But looking back into the Pakistan side, in the heart of the earthquake area, the same little town, it was very interesting to see that most of the population who lost houses lived in rubble stone houses. So one of them here I was able to document, where the builder on the left and the owner is on the right in the picture in the upper right, and they were rebuilding in Daji construction. Now what's interesting about this is that when I was there, The government of Pakistan said you would get no financial assistance for earthquake damage if you didn't build an earthquake-compliant house, which had to be reinforced concrete or concrete block construction. Well, in the rural countryside, that would mean hauling steel and concrete, rebar, concrete block in on mules and horses and maybe some vehicles in order to do that. These people went ahead and did it themselves. In spite of that, well, a year after the earthquake, my colleagues persuaded the government to accept Dudgy construction as compliant. And I felt particularly moved by that because I discovered they used my language from an article written 20 years earlier in the government document that approved it. And then they were doing lessons on how to do it well in the training areas of the NGOs. The Swiss Agency for Development Cooperation teamed up with UN Habitat, and this is just some pictures of those trainings. And now I'm told by my colleague, who's now in Haiti, that there's over 250,000 new houses having been constructed in Dudgy construction throughout this district in Pakistan. And there are a smaller number, an unknown number of them in Batar construction, which was approved about a year later. The bearing wall masonry construction with only horizontal timber lacing is also approved. So that's a rather good side point there, because in fact, one of the World Bank representatives opposed, from what I've been told. I even learned this, that they had a meeting somewhere outside of the country, and they approved this while the guy who was opposing it was out of the country. So there it is. Then the 2001 earthquake in India, which was before the 2005 one, but I wanted to show this because here we have a combination of rubble stone masonry with concrete buildings, and here in Bhuj, it was a typical construction in stone that really failed. And Bhuj was devastated, as was Anjar that I showed in the first picture. But in Ahmedabad, there was timber-laced construction. Ahmedabad was a Muslim city, and Bhuj was a Hindu city. So it's really interesting that the lines of communication carried this system of construction, I think, through a cultural, not a religious, but a cultural connection. Because here you see not a single building that was occupied in the central part of Ahmedabad collapsed. And almost all of them did in certain areas within Bhuj. In Ahmedabad, the concrete buildings, even very high, sophisticated ones, many of them collapsed. So Ahmedabad got the earthquake. It was further from the epicenter, but it certainly got the earthquake. Well, an interesting sideline on that is in central Ahmedabad, there is a Hindu temple. The Swami Narayan temple, mother temple, is in Ahmedabad. Then they have a branch temple in Bhuj, and they used the Ahmedabadian construction for that. There it is, after the earthquake. And the concrete building in the yard there, you see on the right, completely down. It has, if anybody can say that's not a soft story condition, I don't know what is. And there it is, as clean as a whistle. All of those walls above and below are masonry. Timber framed masonry. The Dudgy style of construction. So there you see that pattern, and you take it back and it gives it a nice, it's like a shaking table test on it. So back to Turkey, and you can see what I mentioned before about the collapsing of these concrete buildings, and in among them were these timber frame. You'd never expect something like this to give it credit as a pucca house if it were in India. And there you see how thin these walls are, but it's the flexibility. And that building on the right is not damaged from the earthquake. It's because it was abandoned for 20 years before the earthquake, and people had stolen the materials. It went through the earthquake in that condition. So when we look at this, you can see even a fairly tall building, and we're only talking 3 stories here, but in perfect condition, in a way. If I were on the inside and the wall were plastered, you'd be able to see the pattern of the movement of this building, because that's what you see in pictures where I've shot, how the building really does move. And there's a lot of energy that's dissipated, which slows down the building response, and that's the beauty of this kind of system. Here's an example where the concrete building is not one of these big high rises, so therefore it's not very big, and right next to it is the timber-lace building, and you see how they did. And don't just take the selection of pictures to be an answer. Here is a study that Turkish scholars did where they actually lumped together all traditional structures, including unreinforced masonry, and you see how much better they did across the entire damage district. That was the level of difference. So we're dealing with something here where the answer may lie in this form of construction. I have to bring Haiti into it because there is where it moves off the charts, because we have the downtown of Haiti as an example where the reports of the death toll and the amount of damage is extraordinary. Here you can see every building. And so a kind of survey that would be impossible otherwise. And of course the World Bank funded a mapping of the straight down. You'll see that in a moment. But I then am using the mapping by the World Bank to do this research. So looking at a publication published 4 days after the earthquake by a forensics engineering firm, RMS, Risk Management Solutions, they estimated 250,000 fatalities in this earthquake. And I called him and said, what was this based on? And you could see in the report what they did base it on. And of course, as you know, the death toll has stayed hovering around there in almost all subsequent publications. But in their report, it was based upon USGS shake map. But they don't say which USGS shake map. It's as if all shake maps are the same. Well, I went looking for a shake map. And I found one on Wikipedia that shows a fault trace that goes right under Port-au-Prince. This is Port-au-Prince here, central Port-au-Prince. And you see this is supposedly the line of the break. This is shake map version 7. USGS would not give me a copy. I called them. They only will give you a copy of their latest version. Well, look at the January 12th, the day earlier, the fault trace is more out to sea. That's why they thought there would be a tsunami effect, and there wasn't. And it doesn't get to Port-au-Prince. And the one that's now the current, since March 4th, also doesn't get to Port-au-Prince. So this is paler color. So therefore, under their USGS shake maps, the shaking was less in Port-au-Prince. Now, the modified Mercalli scale is an iterative scale based upon building damage to try to estimate how much ground shaking there was based upon buildings. And based on what you'll see in a moment, I've come up with the estimate that this is actually an MMI 7. Whereas if you go on the internet, you'll see it as high as a 10, which you see right there. It's still published today. And the USGS has it as a 7. Well, look at this. This is a hotel I stayed in. It never closed from the earthquake. Unreinforced masonry, except for rods at the floor levels, and that's the level of maximum damage in that particular building, the Olafson Hotel. And it's in downtown Port-au-Prince, just to the south of the National Palace. And to just prove that shaking did occur at the site, the red circle is the hotel, and the blue circle is a 7-story hotel that pancake collapsed, made of reinforced concrete. Another form of construction, the more usual form of historic construction, is this, which is an infill rubble stone masonry. So it'd be hard to classify rubble stone masonry, even though it's surrounded here by brick, as good quality masonry construction when it comes to earthquakes, for many reasons, I can explain. And as you see, the rubble stone fell out, but the building remained standing. So this would classify as a poor masonry building under the Mercalli scale. Again, these buildings were extant when Giuseppe Mercalli was alive. And then I want to honor our guest, Anushka Mecklenburg, who is the owner of this house. That's on the cover of the World Monuments Fund book. This house is a combination. It's actually well crafted, good quality brick masonry, but behind that masonry is rubble stone. So it falls in the in-between. And that's the level of damage that it had. It did not collapse. And we're now trying to help her and help Haiti save this building. Become an icon, of course, of the earthquake by being on the book. There is another type, which is like the Dajidwari Kashmir, or the Hamish construction of Turkey. Here in Haiti, in French, called colombage, infill masonry. This building had just tiny bits of damage on it, and it is right behind the National Palace. That pancake collapsed. And nearly across the street from here, a rather small concrete building that collapsed. And all of you who have been dealing with this earthquake probably are familiar with the Hotel Montana. And I actually think the collapse of this hotel, which had on its website the most ironically prescient comment from before the earthquake that I've ever seen. Because this was occupied by American government officials almost continuously, I have had friends stay there. I think it helped and was used by USGS to set the damage scale. Because I think it started out as a 9, and they saw this was farther from the epicenter than the Olofsson that I showed you, or the downtown, by about double, and it still was flattened by the earthquake. The earthquake had to be bad. Well, and then of course, we go back to the RMS, and this is where it gets really interesting. They posited their death toll estimate, which has now been embodied in the historical record as the believed death toll, on the expectation that people in the informal settlements, where the buildings are built by the occupants themselves with no training, reused materials scabbed together, but of concrete, would do so badly that it would kill the hundreds of thousands of people. They don't think they had that body count from looking just at the downtown. But what about what I found in the pictometry analysis? Areas and areas upon areas of this where you're hard-pressed to find damage. And the newspaper shots, it's not as if there was no damage, but it just simply wasn't the concentration of damage one would expect to find. And so this becomes really interesting. I then turned to the World Bank study where the red spots indicate damage, and I've tested it in a few places with the pictometry data. And here is rather interesting, a concentration of red spots. And then when I look more carefully, in that particular case, I think it was because the houses were so variegated by their original construction that what looked straight down as a collapse wasn't. And then other areas where it was clearly a collapse, like here, I then created stereo pairs, which are at the bottom there, which across your eyes you can see in stereo. And that way I was able to determine which areas were steep. And almost always I found the damage concentrations were on steep slopes on the left there, where a lot of the news photography focused on that. But when you see things like that on the right, you have to say that earthquake could not have been strong, because that should have been toast. That is not good construction. It's all concrete though. So the idea that concrete is bad is not the point. It's where we go with this. Here we have masonry confined with concrete without any beams along the top. These kinds of buildings would have, in a bigger earthquake, fallen down. So what is interesting is that the poor people building masonry buildings surrounded by concrete, the walls go to the ground. They're masonry wall buildings. They're solid wall buildings. And I think that gave them the extra value. Then a frame building where you don't have the masonry. So look at this, and it really tells the whole story, because you see this kind of detail. You realize that if that was expected to hold the building up in an earthquake, after it goes inelastic, in other words, after it begins to break, there's no way. And yet that's what most untutored reinforced concrete construction turns out to be. And here is an interesting juxtaposition. On the right, you have Haiti, with thousands of pages of words about how this poor country could not have had a sophisticated building industry. But what about New Zealand? which has one of the most advanced seismic engineering communities in the world, from which we get many of our professors in our schools. That's Christchurch, New Zealand, and that after the earthquake, which ended up pancake. And then when I saw this, and then somebody sent me a floor plan, those are the columns of the building. The columns of the building all the way to a central core, and the central core didn't fall down. All the floors were resting on those columns. They were not encased, engaged. They had no shear caps or anything. Those little gossamer columns you saw in that picture are all that held up the building. So here we have a situation where I want to be clear. We're not talking about every building, but concrete construction has brought a new low as well as a new high to quality standards. So at the low end, it falls below core quality masonry when we see these kinds of failures. It has little reserve. It doesn't have any damping in it. So it goes to collapse almost immediately. And we're only talking about poor quality here. So we have collapse at an MMI 7. And then in a place like Haiti, it really is a pyramid in terms of numbers. And if we look at this, we can place these buildings on this plan where you have poor quality and good quality masonry, and at the same time, place the concrete buildings on that. So on the good end of concrete, we have some examples. We have a building that was rolled, God knows how far from its original foundation by the tsunami, and nobody could say that that building was poor construction if it was actually rolled by the wave of the tsunami and ends up resting on its side with the structure intact. Or in Haiti, that pavilion. That's reinforced concrete with a heavy roof and only one shear wall in the whole thing, behind the bar, which was behind me as the photographer. And then you have the other extreme. In Van, in Sikkim, and Haiti, just these three examples. But then on the right there, you see the Digicel building, which falls somewhere in between. It's still standing, it had damage, and it was considered good quality construction. But when I asked an engineer, a colleague of mine, what did he find that were the problems with concrete? This is the list he gave me. It gives you some idea, how do you solve all these problems in Haiti? And it doesn't mean people can't build even in developing countries. That's a Le Corbusier building, but it also shows high quality concrete construction. But this is the standard fare in downtown Delhi. A new building I found, and that's the level of quality. You can't expect that to be seismically sound. But I want to tell you something different. I could go on and on about poor quality construction. I think that's a mistake. That we're really dealing with something where there's a fatal flaw to the system from the very invention of the method of analysis under which it was created. And here is what I want to take you back to. The invention of the skyscraper in Chicago and the invention of the engineering system was a change from simply analyzing each floor, one floor above the other, which then only really works in an analysis if you have an immensely rigid system with a pin connection at the floor level. Well, the invention was improved by coming up with the portal frame analysis based upon contraflexure methodology, where each of these segmentizing of the structure can be analyzed by the three equations of equilibrium, allowing you to build a multi-story building and keep going and have known, not indeterminate forces on each of these pieces. Well, this is a very creative and a very important change that has been maintained in existence all the way through time to the present as a way of designing buildings. And there's nothing wrong inherently in the system except for one thing. Here is how it deflects. Well, in anything other than earthquakes, the whole building is expected to remain within the elastic range of its materials. So the infill walls, the masonry walls, which are not part of the engineering design except by dead weight, are not so much a problem then. But in earthquakes, remember, the thing is expected to yield it, and that kind of S shape to the beams is really an inherent part of its behavior. These tall buildings are a product of that. all the way to the Empire State Building, but they are clad in masonry. The masonry is an inherent part of the first phase of the development of the American skyscraper and of buildings designed with the portal frame analysis. And you see the masonry wall is being built on the Flatiron Building at two places at the same time, so as to avoid creating a bearing wall. So what about the first earthquake to encounter this form of construction? That's 1906, San Francisco, and the fire that followed it. So all of these buildings, the tall ones, were steel framed with masonry cladding. Every single one of those buildings you see there that sticks up high are there today. They've been restored after total burnouts, after the earthquake attacked them first. And as you can see from this, the flood building, which those of you who have been there can recognize here, is still there today. That's the same building. It was totally burnt out. And it has a steel frame behind heavy walled masonry. You would consider that amount of masonry on a building to be heavy and actually make it seismically more risky. But in fact, it is one of the things that, in fact, I think saved these buildings. Now we deal with what we're dealing with today. And Corbusier opened up the whole intellectual discussion among architects by proposing the open floor plans and whatnot like that. Well, that building on the right was in central Goldjuk, and that picture was taken after the big earthquake. But it doesn't yet have its masonry walls. But this is, you don't have a building until you have the masonry walls. This is the more standard form as it's under construction. And how to cope with this masonry panel has been a bugaboo for the last 70 years. And there are many different ways that people have proposed to dealing with it. And here's a picture taken down in Mexico City after the 1985 earthquake. And you see the masonry panel before it fell out completely shattered the column, almost bringing this building down. And in this case, where it didn't even have a soft story to begin with, it ended up with one, luckily just prior to it collapsing. And here in Van, just off the internet from a few weeks ago, is the same kind of thing. Soft stories are created by having masonry above and nothing below, or very little below. Well, here it says it all, because these are two more or less identical buildings. They were at similar heights originally. The one on the left was finished and occupied, collapsed. And the one on the right hadn't had its masonry walls in yet, and so the frame action under which the portal frame analysis is predicated could occur. And the only thing that fell down in that building was the water tank structure in the back, because it had solid walls and therefore couldn't actually bend as well. This is the kind of thing that's been developing around the world in cities. And what was interesting, you see this building. I stopped to photograph this on the way to the Goldjuk earthquake and the way to the 1999 earthquake damage district. And I think every other engineer and architect who went there did so too, because the owner of this building climbed over a barbed wire fence to ask me what I was doing. And I later found out there it is after the masonry goes in. And then I came back later and they were demolishing some upper floors, because I think the reason why that was higher was illegal. So it just gets worse. So this is a fine picture I found off the internet just from the recent earthquake that says everything about where we need to look to fix this problem. It's these infill walls. These non-engineered architectural finishes that are not part of the engineering design of the building. They're treated as dead weight in the building, but they corrupt the frame action. How do you turn them into something that works? Well, my idea is that you can do that, and the way to do that is to look back at the Dudgy construction you see here. And this picture was taken through the window, the third window on the bottom floor of that building on the right, with the collapsed concrete buildings behind it in Adapazari, or in Duzje. What that picture shows is the working of the wall in place because of what I call the subframe, or the armature. And I've called this armature cross walls, because that subframe then holds the wall in place, but it also is predicated on using weak mortar and strong masonry, not concrete mortar, not strong masonry. And so this is how a building would look if you did that. And this is what I found in Mexico City, and right next door to it was that. And the floor levels are visible there. The smaller members are a subframe, in effect. Here in El Salvador, same effect. I wondered why the upper floors didn't pancake too. Subframe. Bam, Iran, steel frame building. The back gone, the front still there. What the hell's going on? I saw that their system of construction is with the steel frame windows put in first. Another building with that finished off, but with no stucco over it yet, or finished brick. The back of the building gone, it had no windows. So with that, I end with Haiti, because you all have seen this with the National Palace and the cathedral. Those were reinforced concrete buildings. The rebar had almost all rusted away. They were over 100 years old. In fact, the U.S. Navy built part of the National Palace. But how many of you have seen that? This is only about 6 or 8 blocks from the National Cathedral. It is equally high and almost as big. How many of you who've been studying Haiti have seen that building? In illustration or in fact? That's masonry construction embraced with steel. Steel imported from France. The behavior of this building, I think, proves the point really well. Do you see any damage? And yet, all of the sheet glass windows that protected the stained glass had broken. That building moved. It was exactly in the damage district between the National Palace and the cathedral and the shore. It's still there, intact, and I think provides a lesson on what can be done to protect buildings in the future as well as in the past. Thank you.